coming from a lot of studies that suggests for large-scale architecture to be of network-centric type, based on a network of elements functionally structured on different layers, all interoperable each other independently of the scale of the system. But we can recognize here the well-known concept of a scale-free network that have been discovered to be well described by a power law distribution of links to their nodes, explaining how the most nodes have very few connections and only a small number of nodes have many connections. The power law describes the number of nodes as a function of their links. The higher is the power n to the x, the faster is the decrease of the number of links per node. This kind of distribution has been observed in the most disparate fields, from the web to biological structure and to the social networks. In the VTM framework, it's expected to be the VTS to assume the role of these accumulation nodes, providing the most of the opportunities of arrangements with other stakeholders. This is true in general and also described in the specific power law of the VTM links distribution. The particular exponent will depend on the final framework architecture. I would like to stress here that about the expected position of VTS that I have mentioned here, I have mentioned it also only because it's pertinent. Of course, it's only a casual coincidence, the fact that my company, Select System Integrati, is a leader manufacturer of integrated systems such as VTS. After that, coming down from the high level of mathematics to the ground of every day, we observe that, yes, the world is exciting because of its diversity, but this is true if you are a tourist. If not, but you are an engineer and have somewhere a system that you wanted to replicate somewhere else, you'll discover that this diversity is not exciting anymore. Therefore, what about standardization? The duct effect is a typical example of something that can be used only somewhere and sometime. But in our case, more appropriate examples are the differences in possible agreements and services. One of those is common reporting system in which Finland, Estonia, and Russia are involved in their common sea area. This is an agreement in the sense intended in the VTM framework, whose results is that each country has access to the databases of the other countries. In fact, once a vessel has reported in somewhere, the operator in that monitoring area simply enters the incoming data to its national database. The two others will be informed too, of course, and this is an agreement. If any violation in the traffic rules is reported, all the countries and area can react. I would like to stress that this is by itself a significant management action. Similar services is also the port state control provided by the Italian Coast Guard in the framework of the Paris Memorandum of Understanding some years ago, for the elimination of substandard ships through a harmonized system of port state control. The existing network of control centers have been verified to be a very efficient means to make that information available in all the ports, also in this case influencing on wide scale the behavior of ships and ship owners. A different element is given by the example of Yemen coastal system, that is in right position to support the traffic security in a very insecure area. The service offered by a long-range automated surveillance permits to move closer to the coast, the safety corridor in which the traffic may be directed to contrast the pirate activities. The ground-based surveillance influences the mission planning of the ships actually engaged for the protection of the area, providing important additional control capacity. The lesson learned from the wide difference among these examples is that not necessarily a normative must exactly drive any of the possible situation. If well conceived, many VTM arrangements may indirectly influence the ships and operators' behavior in the most convenient way for the community. The anomalies detection is another key element for maritime management. That's the following part of the before statement, because we observe that the behavior of any element at sea may be recognized as anomalous only following a cross-correlation among different data sources. For instance, integrating radar, IAS, and satellite position reports, it is possible to realize that a certain ship, such as a pirate mothership, has switched off its IAS transponder. This is a situation that is generally recognized as suspicious. The anomalies detection leads also to the well-known problem of data alignment. Today, the most common information architecture is of net-centric type, but many of the systems in operation since the longer periods are not fully compatible with the new standards. In some sea areas may therefore be difficult to enhance the control correlating or synchronizing ground radar data with satellite synthetic aperture radar images that are now becoming available. A significant example of this is Cosmos SkyMed, which, thanks to the short foreseen revisit time, that's a few hours at full constellation expected in 2011, and the use of advanced synthetic aperture radar technology offers high-resolution images that are expected to permit the desired open sea surveillance. This figure is an example of this. And the most recent of the surveillance systems are ready to use satellite images, also if not yet fully available, relying on imminent reduction of revisiting times that will permit effective surveillance operativity. Satellites are, in short, the new extension of maritime surveillance systems, supporting not only imagery but mainly communications. The satellite repeated IS is one example, but also LRIP is based on this technology. And what happened on board? Are dated to the late 19th, the first studies for the development of radio-linked remote VTS consoles to be used on board for navigation support. When the standard on-board instruments are not sufficient, this may happen for visibility reasons, weather constraints, legal requirements, and so on. The operating conditions of the mentioned large-scale integrated systems has shown a need for extension at sea of the network in order to extend the area in which the services may be provided. The today most used example to introduce this concept of a sea extended communication cluster is the extension of VTS coverage area to support and coordinate the anti-piracy operations. For this purpose may be used a number of onboard surveillance and early detection sensors such as small radars, long-range TV and infrared cameras, or such as satellite imagery and radar, or outer hull CCTV. And the scope is that collecting information from the ships, the VTS acts as a large-scale repeater, forwarding the information to other ships. These information alerts, for example, interested ships that in their area a pirate attack had been signaled by another ship who escaped the attack. It had been observed that, due to their limited autonomy, pirates, in case of failure, try to repeat in short the attack to other vessels in the vicinity. But if those are pre-alerted, of course, the probability of success of the second attack strongly decreases. That's the advantage. And then, concluding, both the lesson learned from all the large systems operated up to now and from the studies and investigations on maritime situation lead to the general observation that information distribution is not a technology problem, but mainly a matter of arrangements among authorities. Technology is now well supporting the opportunity for those arrangements, but many of the implications of this opportunity are felt in different ways in the different parts of the world. That situation leads to a difficulty and a cost for the enterprises because it makes on principle impossible to